All right, today we are going on an absolutely incredible journey. We're talking thousands of kilometers straight down to figure out what's actually under our feet. Yep, we're heading right to the core of our planet. So let's dive in. But here's the thing, right? It's a fascinating problem. We can't actually go there. So how in the world do we know it's down there? How have we mapped a place we can never, ever visit? That's the big mystery we're going to unravel today. Okay, to put this whole we can't get there thing in perspective, get this. 12.2 kilometers. That's the deepest hole humanity has ever drilled. It's called the Kola Super Deep Borehole. Now that sounds pretty impressive, right? But on a planetary scale, it barely even scratches the surface. I mean, it doesn't even get all the way through the Earth's crust, which is the thinnest layer. So if we can't drill, how do we see what's down there? Well, the answer is incredible. Believe it or not, we use earthquakes. Yeah, the very same seismic waves that shake our cities are the tool we use. They act like a planetary-sized X-ray, letting us map the deep interior. Pretty wild, huh? Okay, so our journey is going to start right where we live, on the crust. You know, it feels super solid, permanent, but as we're about to find out, it's actually the most fragile and thinnest layer of the whole planet. You know, I absolutely love this analogy. It just makes it so clear. Seriously, think about that for a second. The entire world that we know, all the mountains, every ocean, it all sits on a layer that if you scale it down is thinner than the skin on an apple. That's it. And that apple skin isn't all the same either. We've got two different types. There's the oceanic crust, that's the stuff under the oceans. It's thinner, denser, and made of basalt. And then there's the continental crust, what we're standing on right now. It's way thicker, but lighter, and made of rocks like granite. So, here's why this is so important. The crust is brittle. When you put it under stress, it doesn't really bend, it breaks, it snaps. And those breaks, which we call faults, are exactly where and why most earthquakes happen. All right, let's head deeper. We're descending below the crust and into the planet's massive engine room, the mantle. The mantle is just huge. I mean, it makes up an unbelievable 84% of our planet's total volume. The crust is just a tiny little fraction in comparison. And here's the crazy part. Even though it's technically solid rock, over geologic time, we're talking millions of years, it behaves like a super, super thick, slow-moving fluid, kind of like tar. And this is that engine room in action. There's this slow churning cycle going on called mantle convection. Rock down near the core heats up, it gets less dense, and it slowly rises. When it gets to the top, it cools off, moves sideways, and then sinks back down. This constant motion is the driving force that drags the tectonic plates on the surface around. It's the engine for the whole system of plate tectonics. Okay, we're taking the final plunge now. Our journey is taking us to its last stop, deep into the most extreme environment on our entire planet, the core. What we find down here is this massive sphere made of iron and nickel. But it's a world of two halves. You've got this turbulent, churning liquid outer core, and inside of that, a completely solid inner core. But hold on a second. How does that even make sense? The inner core is unbelievably hot. We're talking hotter than the surface of the sun. So how on earth is it solid when the layer right outside of it is liquid? It seems impossible, right? The answer is one word: pressure. Just an unimaginable amount of pressure. The inner core is being squeezed by the weight of the entire planet. That creates a pressure that is over 3.6 million times what we feel at the surface. And that immense crushing force literally pushes the iron atoms so close together that they're forced to lock into a solid crystal, no matter how hot it gets. And that liquid outer core, it's absolutely critical for us. Seriously. The constant motion of all that liquid iron acts like a giant dynamo, and it generates Earth's magnetic field. This field is like an invisible shield that protects us and our atmosphere from being blasted away by the solar wind. Without it, life as we know it probably wouldn't exist. So there you have it. We've made the journey from the crust all the way down to the core. But that brings us right back to our original question, doesn't it? How did we figure all this out? How in the world did we map these layers when we can't even get there? Well, the technique has a pretty cool name. It's called Seismic Tomography. And really, you can think of it like a giant CT scan for the entire planet. Scientists use the waves from earthquakes to create a 3D picture of the interior, just by tracking how those waves speed up, slow down, and bend. The key is that these waves act differently depending on what they're traveling through. They change speed, they bend, but here's the real clincher. There's a certain type of wave, called an S wave, that physically cannot travel through liquid at all. And scientists saw that these S waves just stop dead when they hit the boundary of the core. That was the smoking gun, the definitive proof that the outer core has to be liquid. And that brings us full circle to this incredible paradox, right? The very thing that can be so destructive on the surface, earthquakes, is also the greatest tool we have for understanding what's deep inside the planet itself. It's just amazing. Okay, wow, we have covered a lot of ground, literally. So let's do a quick recap of the most important things to remember from our journey. So to break it all down, Earth has 4 main layers. We start with the thin, brittle crust. That's where earthquakes happen. Under that, you've got the massive mantle churning away and acting as the engine for plate tectonics. Go deeper and you hit the liquid outer core, which creates our protective magnetic field. And right at the center, the inner core, which is solid because of that insane pressure. And the coolest part? We see all of it using seismic waves from earthquakes. So we've mapped the deep interior. We know the structure. But that just leads to the next big question. What happens up here on the surface? What happens when those brittle crustal plates floating on that massive engine of the mantle actually start to move? When they grind past each other, pull apart, and smash together? Well, that's where things get really interesting.